Hello, my name is Bill Bowen and I'm a project management instructor here in Ottawa, Canada. I have created this video to provide some background behind the estimating techniques that you are likely to encounter within your project management studies. The video is intended for someone without previous project management experience or formal studies in statistic theory, and gives only an introductory to the various estimating techniques and some of the issues surrounding estimating. This video is intended purely as a starting point on the road of learning estimating. The contents of the video align to the 5th edition of the PMBOK. In reviewing document requirements for the early stages of project lifecycle, you may have already encountered several documents where estimates form key components. During the project initiation phase, the budget and schedule elements of the project proposal, feasibility study, justification, and the project charter are all based on estimates. During the planning phase, these estimates are refined and improved, but often remain essentially estimates. Given that project managers work with estimates so much, students often ask me, where do these estimates come from, and how do I use them effectively? These questions will form the basis of this video. With these questions in mind, let's now look at the agenda for the video. The first topic that I will cover is why do we need to do estimates at all on projects? The next topic I will take a look at is 4 standard estimating techniques that you're likely to encounter within your studies. I'll then look at why our estimates do not always give us the results that we want. And of course, provide some strategies for how best to interpret estimates. I will then look at a very interesting statistical estimating technique called the 3-point technique. And finally, I'll conclude the video by providing 2 examples of how this 3-point estimating technique can be used within project management. So let us begin by first asking the question, why do we need to do estimating at all on projects? To understand this, you need merely to examine the formal definition of a project. It is a unique endeavor, not something we normally do. As such, we often lack sufficient historical data to perform proper statistical-based analysis. Sometimes we don't know all the details about the project, and we've had to make assumptions, and we support these assumptions with estimates. Keep in mind, a project is not part of our regular business model. We may not have all the expertise and experience that we would like when it comes time to prepare our budgets and our schedules. So given the unique nature of projects, we often find ourselves in a situation where exact data does not exist, and we have to estimate durations and costs. Let's now look at 4 common estimating techniques. We'll begin by looking at the one we're probably most familiar with, and that's expert judgment. With expert judgment estimates, we are guided by historical information and personal expertise and experience. There's usually a technical lead or a subject matter expert on the project that we can consult with to find out how long tasks normally take or how much they normally cost. These experts give subjective analysis based on their knowledge and expertise. Our confidence in their estimates is usually based on their knowledge of a particular subject matter. As project managers, we often rely on expert judgment because it's quick, it's inexpensive, and it works even when other estimating techniques lack sufficient information or data to be available to us. The drawback of expert judgment is that it can give inconsistent results that are difficult to quantifiably justify. And a different expert might dispute our estimates, and we have no way to resolve which expert would be correct. And now let's introduce a second form of estimating called analogous estimating. With analogous estimating, you base your estimate on historical data or similar projects that you've done in the past. For example, if your roof needs reshingling and you encounter a contractor doing similar work in the neighborhood, you might ask them for a quick quote on your roof. You might be surprised that they can offer you a quote without even seeing your home or knowing the details about the layout of your roof. This is because they're using analogous estimating. They have worked on similar houses in your neighborhood, and they are using the actual cost and duration from those jobs as a basis for estimating the cost and duration of yours. Analogous estimating is often used when preparing bids or quotes for a new project, or even part of the project planning process itself. By reviewing actual data from previous projects that exist either as part of corporate memory or has been formally recorded within the company's lessons learned records, or alternatively by simply investigating industry trends, a project manager can often find and utilize valuable actual cost and actual duration data from similar projects in preparing their estimates for their new projects. The same sources can be used to obtain an initial understanding of what risks might be encountered or what resources might be required for this new project. This information, combined with the project manager's understanding of the similarities between the new project and the previous ones, might be enough to form the basis for the new project's estimate. The project manager would understand that additional effort might still be required to make adjustments in the estimate wherever differences between the projects exist. The benefits to analogous estimating is that it is less time-consuming and costly than beginning the process from scratch. This technique is frequently called upon when limited amounts of details exist on the new project, such as in an initial ballpark estimating situation. The drawbacks of this method is that the full impact of the differences between the projects can often not be fully recognized, and as such, inaccuracies in the estimates can still be encountered. The next estimating technique that is often studied and utilized within project management is parametric estimating. In parametric estimating, a formula or model is used to calculate cost or duration based on a set of project parameters. For example, if our company builds boxes and it takes us 1 day to build a box, then you might estimate that it would take 2 days to build a box twice as big. This logic is based on the assumption that the level of effort required to build a box scales linearly with the size of the box. While this model might not be valid, and probably isn't, it does provide us with a means to quickly estimate the duration required to build boxes of different sizes. You often encounter parametric estimating in project management. For example, supposing you were asked to host an event for 100 people. After calculating all the costs involved, you estimate that the event would cost $10 a person. Therefore, the overall cost would be $1,000 for the event. However, at the last moment, the event sponsors ask you to accommodate 10 more people. Having calculated the individual cost to attend the event at $10 per person, you estimate that the 10 additional people would cost $100 more. While this model has provided you with a quick means of scaling your estimates to accommodate different size groups, it may have its limitations. The project manager has to understand that it is only an estimate. The model may not be valid, or it might have limitations, or it may not be accommodating all the actual variables involved. For example, adding 10 more people might require a larger room, or additional staff to be hired, in which case the overall cost may be more than $10 per person. Parametric estimating is widely used within project management. It's easy to work with as it can be applied to the whole project or to simply segments of the project. It can be integrated into other estimating methods, and it is easy to explain to the project stakeholders. However, its drawbacks are that it is only as good as its underlying model. Whatever limitations or inaccuracies exist within the model will be reflected within its estimates. The last estimating technique that we'll introduce is a group estimating technique called Delphi. The Delphi technique is a way to harness the combined power of a group to arrive at an estimate for a project. It is often used when other techniques, such as an expert, a model, or a similar project, is not available. The technique is most often used in a group setting, with multiple passes to slowly refine the estimate. Let's explore how it works. The Delphi technique is designed to avoid groupthink, a situation where everybody simply goes along with whoever talks the loudest at the meeting. The way it works is that a group or team is briefed on the project and the task for which an estimate is needed. As a group, they can discuss the task and explore elements that need to be considered as part of their estimate. Then separately, they carry on their investigation and analysis and eventually anonymously submit what they feel is the best estimate. The project manager summarizes the results of the first pass through the Delphi process and presents the amalgamated information back to the group. The group can discuss the results, consider arguments for and against various estimates, and then once again they separate, think about what they have heard, and resubmit a new estimate to the project manager. If the process is working, the results of the second round of estimating should start to show a consensus is being formed among the group. At this point, the project manager should start to guide the group in examining the rationale for the outlying estimates. After the group has discussed the reasons that might exist for variations among the estimates, they break up once again to consider what they have discussed and submit their final estimate. The results of the group's third estimate should be showing that they are converging on an agreed-upon, most likely estimate. Keep in mind, it is normal that within the estimating process to have variation, and this should be expected. But the results of the group examining, discussing, and analyzing the issue should be leading them to an estimated value that is reflective of the group's confidence. The Delphi technique works best in larger groups of knowledgeable professionals, particularly those with a diverse set of skills. And by involving the team and the stakeholders in the estimating process, it will strengthen their commitments to the project's overall plan. One of the drawbacks of this technique is that it is time-consuming and does not always provide the quick turnarounds often sought within project management. Another drawback is that it can divide a group rather than bring them together. There is a risk that multiple camps in the group will begin to form and that no consensus will be reached. At this point in the video, we've looked at why project managers often need to make estimates and introduced 4 techniques for estimating. But as you begin to work with your estimates, you might find that you run into problems, as the estimated values do not allow you to develop a project plan that will run smoothly, and you'll encounter cost overruns or schedule slippages. So before that begins, let's look at some reasons and common mistakes in the way we work with and use estimates within our project plan. In your project management studies, you may have encountered the phrase, estimates are not actuals. But let's look at an example that helps us understand what this actually means. To help us understand this phrase, estimates are not actuals, let us use the following scheduling example. Suppose that your first task as project manager is to interview 4 potential candidates for your team. After asking around, you find out that you should estimate about an hour for each interview. Therefore, you schedule your 4 candidates to be interviewed in the morning, 1 hour apart. In this example, we have used the estimated 1-hour interview duration as our actual interview duration. This approach can lead to difficulties, as each interview is unlikely to take exactly 1 hour. For example, let us assume that the first 2 interviews go smoothly and take a little less than an hour, while the second 2 interviews take a little longer than an hour. On average, our interviews did in fact take an hour each, just like we had estimated. However, variations in the duration of each interview exist, which causes our schedule to slip. While after the 2 first interviews, the potential to be ahead of schedule exists, we are not able to benefit from these shorter interviews, as the next candidate did not show up until their appointed time. Therefore, as you can see in our tracking Gantt, our schedule did not benefit from shorter interviews, but schedule slippages occurred when interviews were over an hour. Thus, our overall interview process took 20 minutes longer than we had expected. Even though the average interview duration was exactly what we had estimated. The takeaway from this example is that when working with estimates, schedules rarely benefit when durations are overestimated, while almost always being impacted when durations are underestimated. It is simply difficult to advance the schedule to the left for a number of reasons. For one, resources are usually already committed on other tasks, and simply because a task is available to be started does not mean you're able to start it. Also, it is human nature to deliver something when it's required and when you've agreed to deliver it. Regardless of when you're allowed to start the task, you will deliver it on the scheduled date. Thus, even when a task is available to be started early, the schedule rarely gets shifted to the left. It might be tempting to attempt to fix these schedule slippages by simply adding buffers, additional time, onto each task within the schedule to accommodate variation in task durations. Let's return to our interview schedule, but this time we will, across the board, add 15-minute buffer to each of interview times, on the hopes that this will keep us on schedule. You often see this strategy with inexperienced project managers who add buffers into their schedule on hopes of developing a schedule that they can actually keep. But in doing so, our overall project duration is now 5 hours, which is longer than the project took when it was unbuffered. Then it only took 4 hours and 20 minutes to complete all 4 interviews. So while simply adding longer and longer buffers to each task would eventually allow us to have a schedule that we could keep under the worst of conditions, it is very inefficient and is not part of accepted industry best practices. An experienced project manager knows there are better ways to utilize estimates within a schedule. Before I move on from the idea of buffers, I wish to point out that adding buffers to a schedule can be part of an acceptable scheduling technique, but it must be done in a very efficient and structured approach. I would encourage you to learn more about efficient use of buffers utilizing the critical chain management of technique described on page 178 of the 5th edition of the PMBOK. This now leads us to our next topic, where we'll examine how we can effectively incorporate estimates into our schedules. To do this, we need some background, and I'm going to draw upon the tools and techniques found within statistical analysis to find ways to help us create better schedules that we have a higher degree of confidence in and whose durations can be logically justified to to our stakeholders. We'll begin by reviewing statistical concepts using the bell curve or the normal curve, and then we'll move on to the beta curve, which, as we will discover, is far better suited to the realities of project management. Let us begin our review of statistical terms and concepts by first looking back at the normal curve, also called the bell curve, as its shape is similar to that of an outline of a bell. You might remember playing the game where you drop lots of marbles through a series of pegs and eventually they form a bell shape. This bell-shaped curve offers us a lot of insight into estimating, which is something that is very important to us as project managers. I hope that you've all encountered this curve at one time or another within your academic studies. While a complete study of this curve is beyond the scope of this course, it will be useful to us in reviewing concepts such as averages and standard deviations. In our example, when we asked for an estimate on how long an interview normally took, we were told that we should estimate approximately an hour for each interview. On our normal curve, I have shown this 1 hour estimate with a blue circle, and as you can see, our estimated duration also represents the average duration for an interview. From personal experience, we intuitively know that while an average interview might take an hour, any one particular interview might take longer or shorter depending on factors such as how many questions does the candidate ask, did the candidate arrive on time, was the interview process interrupted at any point, and we accept that the average duration for an interview does not represent an exact duration. Thus, if all things were equal, it would be likely that half our interviews would take less than 1 hour, and in these cases, by setting our interview duration to be exactly 1 hour, we would have overestimated the interview duration requirements, and we would have completed the interview ahead of schedule. Subsequently, approximately half of our interview durations would take more than 1 hour, and in these cases, we would have underestimated our interview duration requirements. For these interviews, we would experience schedule slippages, and our schedule would slip to the right, which is another way of saying we would be behind schedule. Keep in mind that when we were told that an interview takes approximately an hour, this is correct. An average interview duration is an hour in our example. It's just that in practice, they are likely to be more or less than an hour, which leads us to either over or underestimate the required durations. Of most concern to us as project managers are the cases where we would have underestimated the interview duration requirements. In these cases, we would experience schedule slippages. What is implied within our 1 hour interview duration estimate is the understanding that approximately 50% of the interviews will take more than 1 hour and 50% will take less. So clearly, using the estimated duration for a task as the foundation of a schedule almost guarantees that you will encounter schedule slippages. So what do? One statistical concept in particular called standard deviation is particularly helpful to us. Standard deviation is often referred to as the Greek letter sigma. For example, in the quality approach called Six Sigma, Six Sigma is the same as sixth standard deviation, which in the case of the quality standard refers to producing goods that are 99.99966% error-free, which is what six standard deviations equates to. For our scheduling example, think of standard deviation as defining the buffer you need to add to your estimated value to improve your confidence that the task can get done in the allocated time. For example, if we determine that one standard deviation in the durations for our interviews is 5 minutes, then by adding 5 minutes to our task durations, we would improve our confidence in getting the task done within the allocated time from 50% to 84%. If you're not sure where this 84% value comes from, and you wish to know more, you would need to take a more extensive, in-depth course on statistics to answer that question, which is clearly beyond the scope of this course. For our course, we can simply accept that by adding one standard deviation to our average value, we will get a duration that we can have 84% confidence in. Please note, although I have shown the normal curve standard deviation formula here, it is for reference only. I'll introduce a much simpler and easier to work with formula that will be adequate for our needs. Subsequently, instead of simply adding one standard deviation to our estimated or average task duration, if we were to add 2 standard deviations, we would have a duration that we could be 97% confident of. This new duration would most likely account for all but 3% of our interviews, more than sufficient to cover all but the most unusually long interviews. So these are all the statistical concepts I wanted to review using the normal curve. I've introduced standard deviation and confidence in our estimates, but more importantly, the normal curve has highlighted the fact that in the real world, depending on the situations, tasks usually have a range of durations that they can be completed in. But while the normal curve is great for demonstrating these basic statistical concepts, it is not a practical curve for us to use within project management for several reasons. The first reason is the number of observations required or the amount of historical data that is needed for the bell curve to be fully understood. If you've ever played the ball game where you build a normal curve by dropping balls through a series of pegs, you know that you need to drop a lot of balls through the pegs before you get anything that looks like a bell curve. While it works, you can build a curve. All those data points are needed before the shape of the curve appears to the point where you can use the formulas to calculate its standard deviation. But as project managers, this is a problem. Projects by definition are unique. We often don't have a lot of data points to work with, such as how long a task normally or historically has taken. As such, we need a curve that will allow us to calculate standard deviation with very little historical data. If we are going to use statistics as the basis for incorporating our estimates into our schedules, then we need a statistical model that can accommodate what we will encounter in real life. In real life, while it is likely that a task might be completed early, it is unusual for that task to be completed really early. And while it is also likely that a task might be completed late, it is not really that unusual for that task to be completed really late. A number of reasons exist for this. The simplest one is to acknowledge that it is human nature not to finish tasks early. If you give someone additional time to complete a task, then they will most likely place a lower priority on that task and shift their focus to some other task that has a more pressing deadline. And as such, we need a model that reflects this reality. Fortunately, one exists. Now that I've reviewed a bit of statistics, I would like to introduce a curve that we will be using the 3-point estimating technique, which is a technique for incorporating estimates into both our schedule and our budget. In the PMBOK, you will find this technique outlined on page 170 for schedules and 205 for budgets. Let's begin with the normal curve and see how it would have to be modified to make it more useful to us as project managers. If we shift the normal curve to the left to reflect the fact that we are more likely to underestimate a task duration than we are to overestimate it, then the beta curve emerges from the normal curve. This beta curve is a much better model for us. Let's look at why this is. As with the normal curve, in our beta curve, we assume that our estimated value represents the most frequently encountered duration. But unlike the normal curve, where we have an equal chance of under or overestimating, the underlying premise of the beta curve is that we don't usually overestimate a duration by very much, but we can underestimate it by quite a bit. This is shown by the fact that the range of possible durations to the left of the estimated duration is much shorter than the range of possible durations to the right. The larger range of possible durations to the right of our estimated value indicates that we have a potential to underestimate a task duration by quite a bit. The major difference between the beta curve and the normal curve is that with the beta curve, our estimated or most frequent duration and our average duration are not the same value or the same point in the curve. We still assume that when we ask for an estimate, we will be told the duration that is most frequent or most likely encountered. But this is now different than the average duration, when we account for the fact that some durations will run considerably longer than we had estimated. This means we have a lower confidence in our estimated value, and it no longer reflects our average duration. To proceed, we need a formula for calculating average durations on a beta curve. But we are fortunate in that the beta curve, there's a relatively easy formula for calculating the average duration, or the duration that we would have 50% confidence in. So let's look at this new formula as the first of two formulas we need to learn about this curve. The formula for calculating the average duration on a beta curve is simply to take 4 times the estimated value plus the most optimistic estimate and the most pessimistic estimate and divide the resulting sum by 6. For this course, we're not going to investigate why this formula works. Instead, we're simply going to assume that it is correct. If you wish to understand more about the background and rationale for this formula, then I would encourage you to take a more in-depth look into the field of statistics. But what we will do is take a look at the 3 estimated values that we need to make this formula work. These are the estimated value, which we've encountered before, the optimistic and pessimistic values. The point on the graph labeled M is our estimated value. We've encountered this value before. It has most likely been obtained through one of our estimating techniques that we looked at earlier in the video, and it represents the most frequent or likely duration. Next, we look at the most optimistic estimate, which is shown by the letter A on the graph. This estimated duration represents the shortest duration that a task, or in our case the interview, is likely to be or could reasonably be completed in. A more formal way of looking at it would be that 99% of interviews would take longer to complete than this estimated duration. So it represents a situation where everything goes smoothly as possible. No delays of any kind are encountered. In our case, we've assumed that the best we could ever be able to do is wrap up the interview 5 minutes early, so that the overall duration is only 55 minutes instead of the full hour. The final value that we need for our formula is the pessimistic duration. This duration is represented by the letter B on the graph. The pessimistic duration represents the longest that an interview is ever likely to last. This is a situation where delays are encountered, the interview candidate arrives late, asks lots of questions, and the overall process is interrupted as often as it possibly could be. Again, a more formal way of looking at this is that it represents the maximum duration that all but 1% of the interviews would ever last for. As you can see on the graph, we've assumed that the worst case, the meeting will last for an additional 20 minutes beyond our estimated duration. We have now defined the 3 estimated values that our beta curve needs to determine the average interview duration. Unlike the normal curve, where we needed lots of data points to figure out the estimated value, with our beta curve, we only need these 3 estimated values, which, in practice, are fairly easy to obtain. With them, we can calculate the average expected duration for our tasks, or in our case, our interviews. Remember, we have estimated that interviews most frequently take 60 minutes, but when you factor in the durations of all the interviews, we find that the average duration is slightly longer than the 60-minute durations. Entering our 3 estimated values into our formula, we find that the average interview duration would be closer to 62.5 minutes than the most frequent duration, which is only 60 minutes. The beta curve makes it fairly easy to calculate the average duration, but it is unlikely that any project manager would be comfortable basing their schedules on durations that work only 50% of the time. Doing so would almost guarantee schedule slippages will be encountered. But as with the normal curve, we can improve our confidence in our duration estimates by adding 1 standard deviation to our task's overall duration. This would give us a resulting duration estimate that we would have 84% confidence in. Again, we are fortunate that with the beta curve, the standard deviation formula is quite simple. It is simply the most pessimistic duration minus the most optimistic duration, and then divide the resulting sum by 6. So let's put the numbers into our formula and see how much of a buffer we would need to add to our average duration before we would have reasonable confidence in our numbers. Using our formulas, along with our estimated durations, we find that the standard deviation for our curve is 4 1/6 minutes, which means if we wish to be 84% confident in our estimated durations for our interviews, we would need to add this 4 1/6 minute duration buffer to our expected duration of 62.5 minutes. The resulting 66 2/3 minute duration would give us a higher degree of confidence that our scheduled duration could handle the most variance that we would expect to encounter in this task. Obviously, in practice, you would round these estimated durations up to something a little bit more easy to work with. But while an 84% confidence in our estimated duration is quite good, a 97% confidence would be even better. Let's see how we would calculate that. We could achieve this higher degree of confidence by simply adding a buffer that represents twice the standard deviation to our original average duration. If we do that, we would find that we should schedule our interviews to last 71 minutes, and in doing so, we would most likely be able to accommodate all but the most unusually long interviews. So this is the last of the new formulas that we need. If needed, I would encourage you to pause the video and replay or review any section that you wish. We're now going to proceed using these formulas and concepts in a few examples. So you might be curious, if we were to go back to our interview scheduling example and use our new duration of approximately 71 minutes per interview, how would that turn out? Well, by scheduling approximately 71 minutes per interview, it would take 4 hours and 43 minutes to perform all 4 interviews. But the good news is, by the end of the 4th interview, we would be on schedule. So how does this compare with the previous two approaches to scheduling the interviews? If you recall, in our first attempt, we simply used our estimated duration of 60 minutes per interview as our scheduled duration. But the process did not keep to schedule, and in the end our schedule had slipped to the right by 20 minutes. Explaining such schedule slippages to the stakeholders can be difficult to do. Next, we tried arbitrary buffers. With our arbitrary buffer approach of simply adding 25% buffer to each task, we were able to stay on schedule, but the overall duration of the process took 40 minutes longer than if we had simply used the actuals. While we did manage to stay on schedule, explaining the need for such arbitrary buffers can be difficult to justify to the project stakeholders, and rightfully so. With our 3-point estimating technique approach, we were able to once again stay on schedule, but the process only took 23 minutes longer than when we had used actuals. This method kept us on schedule while avoiding unnecessarily delays that would have been induced by the arbitrary buffers. Plus, unlike the arbitrary buffers, it is based on sound statistical practices that can be easily explained and justified to the project stakeholders. What's more, were we to continue to do even more interviews, the efficiency resulting from the 3-point estimating technique would continue to improve. That completes all the information I wanted to present on estimating methods and the 3-point estimating technique in particular. In the last section of this video, I want to take a quick look at 2 standard 3-point estimating technique problems that you might encounter within an academic environment. The first one will be on estimating a project's overall duration. The second one will be something completely different, which I have included to show you the range of applications that this technique can be used for. It will be on estimating long-term profit. A typical 3-point estimating technique problem will present you with a series of tasks along with their dependencies and optimistic, pessimistic, and most frequent duration estimates, such as I've shown you on this table. I've also included a Gantt chart just so you can visualize the task dependencies. The question will usually ask you to estimate the overall duration of the project. Let's see how that's done. The first step in the process is to calculate the expected duration. This uses the formula that we encountered earlier of taking the optimistic estimate duration plus 4 times the most frequent estimated duration plus the most pessimistic duration, then dividing the overall results by 6. In this slide, you can see that I'm working my way down the table, and I've included the calculations necessary to figure out what the expected value for task B would be. This slide shows the remainder of the expected duration values filled in. After completing the expected duration column, the next bit of information that we need is the standard deviation for the curve. If you recall, the standard deviation is simply the most pessimistic duration, subtract the most optimistic duration, and then divide the results. As you can see, I've shown the calculations for task B on the screen here. I have now completed the calculations for the standard deviation for each task, and I'm ready to move on with my table. The next column that I need to calculate is each individual task duration that I would have 97% confidence in. This information is needed to solve the original question. Remember, the question asked us to determine the overall duration for the schedule, a schedule that we would have 97% confidence in. And to do this, we need to have that level of confidence with each individual task's duration. Fortunately, the values in this column are easily calculated. They are simply our original average value plus 2 standard deviation, as you see I've done here with task B. My table is now filled in, and I have now calculated all the values that I need to solve the problem. Since we are looking for the overall duration of the project, you might wonder if that is simply the summation of the durations for the individual tasks. But this is not the case. Remember the task dependencies. Some of our tasks are done in parallel and are not on the critical path. The duration of tasks that are not on the critical path does count towards the project's overall level of effort, but not towards the project's overall duration. If we once again look at our Gantt chart, we see that only 3 of the tasks are actually on the critical path, and thus contribute to the project's overall duration. Therefore, in determining the overall duration for the schedule, we only need to consider the duration of these 3 tasks. If we add up the duration of each of these 3 tasks, we get an overall project duration of 24 days. This type of problem is probably very similar to the ones that you will encounter within academic studies of this technique. In our next example, we will look at how our technique can be used to determine long-term profit. Let us suppose that our company supplies goods to other businesses. These businesses place lots of orders with us, and we need to deliver the goods at some point on the 7th day. Furthermore, let's suppose that we have two different ways to deliver on these orders. Our preferred way to fill orders is to get the raw material that we need from our wholesaler. If we do this, then we get a $1 profit on each item we deliver. But our wholesaler is not perfect. Most frequently, they can get us the raw material that we need within 3 days. They have even been able to get us the material in as little as 2 days. However, in the rare case, when they run out of inventory, it sometimes takes them up to 16 days to get us the material. When they do deliver the material to us, we can get a $1 profit on each item we supply to our customer. For simplicity, let us assume that once we have the material, we can get the finished goods to our customer instantaneously. In the event that our wholesaler is not able to supply us the raw materials that we need in a timely manner, we are able to purchase whatever materials we need from the local retailers without any delay. But, given their price markups on the material that we need, we would have zero profits in this case. So given this business model, over the long term, assuming lots of sales, what would our profit be on each item sold? Despite how unusual this question sounds, it is simply another application of our 3-point estimating technique. Given our wholesalers' pessimistic, optimistic, and most frequent estimates, we are able to calculate the expected duration and standard deviation for a raw material. In our example, the most frequent delivery occurs on the 3rd day, but the average delivery duration is 5 days. We could then calculate expected delivery durations that we would have 84 and 97% confidence in. What we find is that in the long run, our wholesaler should be able to get us the raw materials that we need to meet our hard 7-day turnaround time for approximately 84% of our orders. This means that our wholesaler could fulfill 84% of our orders, and we would make $1 for each product shipped. The rest of the time, while we could still fulfill our orders, our retailer would have to supply us the raw material, and we would make no profit. So over time, if we consider all orders, we would realize that we are actually only making 84% per unit sold in the long run. This problem gives us a glimpse into the diverse nature of problems that can be addressed with a bit of knowledge on estimating techniques combined with the 3-point estimating technique. And thus we come to the end of this video. We have looked at estimating techniques, explored shortcomings of using estimates as actuals, reviewed some basic statistics, and learned about the 3-point estimating method and applied it to 2 problems. What I hope you take away from this video is that estimating is not the same as guessing, estimates are not actuals, and understanding of statistics, even a basic understanding, can be a very valuable tool to a project manager. So once again, my name is Bill Bowen, and if you're one of my students, I look forward to providing you feedback on your assignments. If you're not, I hope you found this video to be helpful, either in your academic pursuits or within your career itself. If you enjoyed the video, I have lots more on different project management topics. Feel free to check out my channel.